Hello students, welcome back. Now we are going to talk about another register, and that is serial input parallel output. So in this video we are going to talk about a serial input parallel output register. We will design it with flip-flops, and we are also going to implement it without flip-flop using behavioral coding style in Verilog, so that we know both the aspects. So let us get started. So first of all, let us know that what are the specifications of a serial in parallel output shift register. There is going to be only one bit that will be our input bit. If it is a 4-bit register, we can have 4 bits as the parallel output pins. If it is 8-bit, we will take 8 bits. Only one directional shift will be possible. That means either you can load the data from the LSB or the MSB, and the data will be shifted towards the opposite end. And once the data loading is complete, then we can read it in the parallel pins. How many control cases are going to be there? Let us have a look at those. We need to perform one simple operation. Load the value of serial input at every rising edge of the clock. Valid output will be accessible only when all 4 bits are loaded. That means we have completed 4 clock cycles. More features can be added based on the requirement of the user. Now let us have a look at the block diagram of serial in parallel out register, which is designed using the D flip-flops. So we can observe that there is only one input pin. Okay, then the clock of every flip-flop is having one single clock signal. That means all of them are synchronized. So whenever we are going to have the rising edge of this clock, this input will be loaded, but this will be loaded only when we will shift the output from here to here. So we will be transferring the data in this, and because this flip-flop is getting the same clock signal, it will happen by its own. We don't have to trigger any extra signal. Similarly, this flip-flop will also be triggered, and this value will be transferred here. Similarly, this value will be transferred here. Now after the 4 cycles are complete and we have 4 valid bits at all the 4 outputs, we can read them on these 4 ports. So this is how a serial in parallel out register will work. We can also design it in such a way that we can take input from this side, which will come to this flip-flop, and then the outputs are transferred from this to this and in this way. So left shift or right shift, both of the versions can be designed. Now we are going to implement the same using behavioral coding style in Verilog. So here is the code. What we have done, we have taken one input port which is D in, there is clock and there is load. Output is a 4-bit register which is Q. Now we take one more temporary register of 4 bits, and then we say at positive edge of the clock, this is begin and this is end. Okay, this is the code which will run with the positive edge of the clock. Okay, this line is outside that. Then what we say, if load is equal to 0, that means we are not enabling any new signal loading, any new data will not be loaded. In that case, keep the value of temp as temp. And what is temp? It is an undefined register. If you want, you could have defined the value here, but right now we are saying it is undefined value. All the 4 values will be X. Otherwise, that means if load value is 1, we are taking new values from D in, then we say 4 bits of temp will be concatenation of 3 bits of temp plus the new input. The new input is loaded on the LSB side. You could have loaded them on the MSB side also, and you could have written D in comma temp of 3 to 1. This is all fine. It is all up to you which direction you want to implement. Now we write the test bench and we say this is my test bench. D in, clock and load, these are register. Wire is 3-bit Q. I have instantiated my module and I say at every 20 nanosecond the clock will flip. Then we start the allocations. We say clock is 1 and load is 1 in the beginning. At 10 nanosecond delay D in is 1. After 200 nanosecond D in will be 0. Then another 250 nanosecond delay we will change the load to 0. That means now we will keep the value same, and then again we are changing D in to 1, and then we finish. Now let us have a look at the waveform. So here is what we have. This is our D in, which is initially 1, then it is 0, and then again it will be 1. Clock is always changing. This is load signal. Until load is 1 we will load it, and then when it is 0 we will hold it. So we start loading at the first positive edge. So you can see the LSB is loaded with the value of D in. The D in value is 1, so we get 1. Then next edge one more value is loaded, next edge one more, and next edge one more. Now all 4 values are loaded and we get 1 1 1 1. Till that point we were getting x 1 1 1 and with the value of x. Now at this rising edge again we are loading 1, so the value remains same. At this rising edge the value of D in is 0, so I have started loading 0 from the LSB. 1 0 comes, another 0 comes, another 0 comes, and then what we see at this point, it is all zeros. This point it is all 0, and here we are just holding the value. Okay, we are just holding, and at this rising edge, although the D in is changing to 1, but we are not loading it, we are still holding the 0. So students, now we have discussed registers. Let us get started with one more sequential circuit, and those are called counters. We'll talk about counters in our next video. Keep learning. Thank you.